Alright, hell yeah. So I just spent 3 hours at the coffee shop going over the first three sections. And so what this is analysis of stress and strain, and it sets up the equations that will become the Mohr circle. So this gets you up to that point, and there's quite a bit of math involved. And so this is material mechanics. This book you can get online with a download, pdfcoffee.com. Anyway, material mechanics, James M. Gear. So what I want to do is dive into the mathematics. And let's see. Oh, 558. All right, so and we're going to go through sections 1 through 3. So the introduction, plane stress, and then the principal stresses, and then the maximum shear stresses. And these equations are difficult enough, and then you can link them together with the Mohr circle by turning the equations into the equations of a circle. It's kind of fascinating, but I think this gives you kind of the foundation, and it's a lot of math anyway. It's probably too much math for most people. So cool. So we're going to analyze, in material mechanics, you have stresses that are either in tension or compression, and you also have shear stresses. So these stresses are pressures. The ones in tension and compression are easy and obvious to understand, getting pushed in or pulled apart. Pressures like dropping something in the ocean or taking a spaceship to outer space and the vacuum of space gets pulled apart. But shear pressures, pressures on a surface, you imagine it as sticking a stick of duct tape on this surface and then pulling in this direction. So it's kind of a leveraged pressure. Pressure sideways doesn't exist in fluid mechanics, I don't think. But in solids we give it a name of shear pressure, shear stress. Cool. So what we want is to do these three things. Like in our analysis, we can know there's the tension in a bar. Maybe something's compressing that bar as well. And maybe there's a shear force that's causing shear stress in some sort of beam or bar or whatever. Anyway, and so when we do our element, we're just going to maybe take it with the x-axis being this way, the y-axis being up, and the z-axis being out of the page. And we're going to get values for these. But then in the earlier chapters, we sorry about the phone ringing, holy Toledo. What we did is we had like a bar where you just pulled on it in tension on both sides. And what we found with a steel bar is that, hey, at a 45-degree angle, it might shear because steel is only the pressure that fails steel is half the pressure that steel can take in tension. So steel is really strong in tension, not as strong in shear. Other things that are strong in tension and not strong in shear is wood, especially if you're compressing it. The fibers can do pretty well in tension, but the fibers don't do very well. Well, actually, don't quote me on that, but what happens is that in shear, wood is pretty weak, shearing through it, where it's actually pretty strong in tension. So I said that wrong. Actually, wood, the fibers in wood kind of hold up like straws. So if you have a 2x4, that's why you kind of use a stud wall. It can take a vertical load. But wood actually can't, take a shearing load very well. And so, cool. So if you pull on something, it's going to, at a 45-degree angle, it might rip apart. And that's because when we, so that's just what happens. And we can analyze that by taking an element and rotating it at a certain angle. We can just choose this angle to be 45 and see what happens. But if we have tension, and then if we have a normal stress in the x direction and normal stresses in the y direction and shear stresses, well, there's going to be a certain point where some of these are maxed out. You know what I mean? And when the shear stress is max, or how do we say this? When the shear stress is 0, the normal stresses, one of them is going to be maxed. And the normal stresses added together, well, I guess I don't want to get ahead of myself, but that is true. One of them is going to be maxed. So there's an angle where one of the normal stresses is going to be a maximum. So that's what we're going to be able to do with the equations. The other thing that and when that happens, that's when the shear stress is 0. And at that angle that makes one of these a maximum, we can determine what the angle of the max shear stress is because it's just 45 degrees offset. And because that's going to be a maximum for the shear stress, or how do we say this? Shoot, I'm kind of losing it. But the shear stress will also be another maximum at 90 degrees to that. So if we find, so that's the whole idea for this chapter. So we should probably get into the equations, but we can rotate this element, and one of these is going to become max. So if we just analyze anything and we get a number for this and a number for that, we might want to rotate it to see if one of these goes to a maximum. Now, maybe in the way the geometry is as is, maybe one of them is a maximum, and if we rotate them, they actually become less. And so that would mean that this would be the principal axes when this angle is 0. But if these are a number and we have a shear stress, chances are we'll have to rotate this at a certain angle. Well, and especially if you have that just spells it out too. I mean, there's a lot of take homes from this that are just oh yeah, because you can get so wrapped up into the numbers, where if I do have a normal stress in the x and a normal stress in the y and a shear stress, by definition there is going to be an angle where the shear stress goes to 0, and at that angle, then one of these is going to be a maximum. And so that's cool. And then we can know where the shear stress is going to be maximum, because once we've found the angle that one of these is a maximum, we're going to be adding 45 degrees or subtracting 45 degrees from that. Sweet. Okay, so, all right, so then what we need to do is turn this into we need to we're gonna get these as a given. We can find these from our conventional ways of free body diagrams and finding axial loads and compressive loads and shear forces on an element. So we can find all three of these. What we want to do is be able to find those maximums given this angle. And so we need to have a way to input these and then output these. So that's the big equation that we're going to use. And how we do that is we make a slice somewhere. And so one thing that you could think of is if I turned this into a 45 degree element, so totally rotated 45. I'm just going to try to draw this in at a 45. I need a stylus, but that's the whole reason we do textbooks, is because when you're reading textbooks, hey, that's all you got. You know what I mean? If you're reading it, you can write on paper to kind of figure out what they did. But the whole idea is they gave you enough information to kind of mentally do it yourself. But anyway, so if we have this element at a 45, we need to find the stresses on that element and the shear stresses, normal and shear stresses. And so how we do that is we can say that, hey, let's do this face first. How would we do that? Well, what we would do is we'd come in here, and if we're looking at a 45, I would just take a line right through here at a 45. And then I would lop off this side, and I would keep this side. And then what we do is we turn it into a free body diagram. These are just stresses. And so this chapter says that, hey, even though that these are stresses and these are vectors, but they're not vectors. They're stresses and they have arrows, but they do not add as vectors. You can't use the parallelogram method to add these because they're associated with the area they act on. And so I guess they call them tensors. And so that's all the introduction chapter said. But anyway, so we turn these into vectors by multiplying by the surface area they act on. So this cube, we're just going to say, has 6 faces, and each of these faces has an area A0. So that's kind of what they use. And so if this stress would turn into a force by multiplying by the area. A stress is force per unit area, or like PSI, or newtons per meter squared. That's a force divided by an area. And then we're going to multiply by an area to get the force. So the force right here would be sigma x A0. This force down would be tau xy A0. This force over would be tau xy A0. This force down would be sigma y A0. And then we would cut at a 45, and we would have a normal force and a shear force. And if we turn this into a force diagram, hell yeah, then we can just sum the forces in the directions that we want. What you do is you set this direction as your, maybe your x direction. We call it x1, and we sum the forces in that direction. And then we sum the forces in this direction. So we want to find the normal force that balances this, and you can see that if we had these two are going to add in this direction, and they're going to be at 45s. So we're going to have 70% of this and 70% of that. So we're going to have basically the square root of 2 in this direction due to these two forces. And then these are also going to be in this direction. Is that right? Hopefully I'm not just totally messing this up. But anyway, so then from that force diagram, you would be able to find these forces. But these forces act on this cut area, which is larger than just the area of this face. This area of this face has the same thickness as this height and width. And so if we cut at a 45, and we have to say that, hey, even though this is just a side view, so this actually is a cube that goes into the page. So if we cut at this 45, that surface, it's like cutting right here at a 45, and then lopping off this side. That area is going to have an area that's the square root of 2. You know what I mean? It's going to have square root of 2 area, and what we find is that so in this case, like, these would be additive, and we would have quite a bit in this normal direction, and in the shear direction, if these were equal, you know what I mean, then we wouldn't have any shear. So at the 45, we would have, if these two are equal and we have shear, then I think that's kind of what it looks like, because if I cut this at a 45, we have very equal, so we have all normal and no shear. And so, hell yeah. So then we just found the we can find the stress on that face by taking the force from that force diagram and dividing it by that area of the square root 2. Anyway, so that was just kind of an overview. We might as well look at what they do to get this. Now we're just going to say, hey, we just have some arbitrary angle. And things to keep in mind for this. If we know the shear stress on one side, it's associated with a shear force. And this little element, and it's infinitesimally small. So a couple things happen when this is infinitesimally small, is that this side, like in tension, is equal to that side in tension. Because there's problems where, hey, if you're have like beams and stuff, or things that are loaded. Anyway, there's a lot of diagrams where your axial loads, your compressive loads, your shear loads are not continuous. You know what I mean? They actually vary over the x direction and the y direction. But what this says is that this element is so small, it's kind of like a differential element. And because it's almost representing what's happening at a point, the stress on this side is going to be the same as that side. Even if there is a differential difference between this side and that side, we're saying that this stress is so small that, that it's the same. And I think this is very similar to calculus, where if you have like a differential slice, like a dx, and you say it's x away, you can put that x arrow to the edge of that dx. It should go through the middle, but that dx is so small that that distance to the edge of that differential element is the same thing as the distance to the center. So that's what we're saying if this is an infinitesimally small element. The smallest I would think of this is if it was like 8 elements of iron packed in here. You know what I mean? So you'd have a cube. A cube would fit 8 spherical, like ping pong balls or whatever. And so you could visually see that and represent that. And maybe that would be a decent way to visualize a very, very small but not infinitesimal. I think when you're trying to visualize something infinitesimally small, that always gets me in calculus, because it's like, you can't fathom infinites anyway. So yeah, like why would you even anyway? So just get really small and who cares? I don't know why I get hung up on that infinitesimal, but I do. I like to have things small, but something manageable, or something that I can actually envision. And I think packing this full of 8 iron atoms would be something that I could envision. And that'd be pretty small. Okay, so cool. So then the idea is to, so this has depth into the page, and we're going to rotate it, and we're going to try to find all of these based on, spam calls. Anyway, so how we do that is we rotate the angle up from the x-axis, and then we have to find, whatever forces we're trying to find. And so here, hey, this is our angle up from the x-axis. We're going to try to find these forces on that cut. So how would that look? So from this picture, you can't really do it from this picture, but you would have to come up to this picture and say, if I'm going to have if I'm going to rotate this axis up and then do a perpendicular cut through here, the place that makes the most sense to take that cut is right on this edge. You could do it anywhere. It really doesn't matter. Like the worst place to do this cut would be, the reason you do it here is because, hey, this area on this side, and again, this is a three-dimensional triangle. Like, we made a cut, and we have this block. And we know that this area, even though it's just a line, it still has the same depth as a three-dimensional object, that three-dimensional cube. This line is actually shorter, though. So this would represent A naught, that initial area. But this, because this angle might be a sliver of an angle, this dimension is not A naught anymore. And so it's A naught tangent of the angle. And we'll go over that in a second. But this angle is smaller. But if we take, and this is stuff to have this stuff set in, it is useful to run through the math and take slices at harder locations. Because if I rotate this up and I take the slice from here, what happens is that I have the forces of this. This is going to be sigma y A naught. That's going to be the force. This is going to be tau yx A naught. You know what I mean? The stress times the area. So all four of these are easy. It's just these stresses multiplied by A naught. But then when we get up to here, we have to figure out what this area is, and we have to relate it to this angle. So, hey, I could figure out what this little slice is, and how I would do that is if this is my angle, theta, and this is what I know the cosine part, and I'm interested in this part, then I would say theta, I would say tangent of theta on this side of the equation is equal to the opposite over the adjacent. I want to know the opposite, and so I would do tangent of theta is equal to what I want to know, the opposite, divided by the adjacent, and get the adjacent, what I already know, over here. So this angle is going to be A naught tangent theta. So that's how you would do that. And then, but if we took our cut right here, we're going to lop this part off. So we want to know this force, this shear pressure, this shear stress only acts on that remaining area. So that remaining area is A naught minus A naught tangent theta. You know what I mean? So your math just gets a little bit more finicky. But in the end, the normal forces that you will get in this new x1 direction are going to be the same. So let's take a look at how they make this cut. And so I gotta get some water. So from the math perspective, is we need to know the area after we make this theta slice, we need to know this area. And so we say the tangent of this angle is the opposite, what we don't know, divided by the adjacent. And so we have tangent of the angle on this side equals what we don't know. I'm going to put a little box there, divided by A naught. So let's get A naught up here. And hey, we now have the equation for this. It's going to be A naught tangent theta. Cool. The other area that we need to know, because these are the stresses, and these are what we're trying to find. We're given these. So we're given this normal stress in the x direction, normal in the y, and the shear stress. And I think I already mentioned it. From equilibrium, if we know one shear stress, these are equal. So you'll see this equation that if we know tau x1, y1, we know if we know one shear stress, we know all four shear stresses. And so the other equation is if we know tau xy, that has to equal tau yx. And that's because if you turn these into forces, we would have an upward force here that has to be equal and opposite on this downward force. And so these two would be this equal and opposite. That would cause a moment. These are a distance, the same distance away, so these have to be generating a moment. And these forces would have to be the same, and these forces act on that same A naught area. So stress is force divided by that A dot. And so all of these stresses have to be the same. So tau xy is going to be tau yx. So for the convention on this is that if this is a positive x face, so how you read this shear stress is this shear pressure, this shear stress is on the positive x face and is in the positive y direction. This one, they don't spell it out. I would write this tau negative x negative y, you know what I mean? Because that might help you. Because this is the negative x face, and then the arrow is actually, this is the positive y direction, so this arrow is in the negative y direction. And so the convention says is that if you have positive positive or negative negative, that's going to be a positive shear convention. And so the shear convention is rotating an element. No, damn it. Shear convention is just what I just said. It's nothing more than that. Because this shear force has to be coupled with this shear force. Or basically, these two are generating a torque that have to be balanced by these two. Because the shear pressures act on the same area, are synonymous with a force in those directions. And so this is also a positive shear. It's on a positive y face, ty, tau y, and it's in the positive x direction. And so that is why you can't have a convention that says, oh, this shear force wants to rotate this object counterclockwise. Let's use right-hand rule, because this shear force, or this shear stress, wants to rotate the element clockwise, and we're calling this positive. So it's always, a lot of people don't go over that of like, cool, you have this convention, but like, why couldn't they have made it easier? Or like, why is this the rhyme and reason? And I think a better question is, why can this be the only way that we describe the convention? And there still is the idea that we still have to, for this one, you still have to choose whether you want to call this a positive shear, so it's at least convenient that we say positive x face, positive y direction is a shear. If we did it the opposite, we would have to say, hey, if I had a positive x face, then if this was in the negative y direction, we could call that positive shear, but you can see how, hey, this is a pretty good convention. And again, this shear is like, if you're looking at rotating it, this is trying to rotate it clockwise, and this is a positive shear. This shear is trying to rotate it counterclockwise, and this is a positive shear. So we can't use the idea of rotating something in a particular direction to indicate positive shear when it comes to this. Man, don't quote me on that, because I swear in chapter 2 they use a convention where they're just like, yeah, let's just say shear is something that rotates an object clockwise or something like that. And I'm just like, huh. And that does come into play when it comes to vertical shear stresses. Like in a beam, all we're interested in is the sign convention for vertical shear stresses. Because if this was in a beam, like this shear stress is trying to rotate this thing counterclockwise. So this shear stress would be associated with a shear force that's going to, this would be a negative shear stress. No, you can't say that. This would be associated with a negative shear force, because if this force was being upward in a beam, a shear force that causes counterclockwise rotation, positive right-hand rule, that's going to be negative. And so for beams, but that only applies to the vertical component. Again, that same thing is going to happen. If we say that this is a negative shear, and it's because it rotates it counterclockwise, that negative shear has to be coupled by a shear force in this direction, in the lateral direction of a beam. And so, and that is trying to rotate it the opposite way, but we're still calling that a, like in a beam, this, yeah, so you would have to call that a negative shear force, because it's trying to rotate, or that would be a positive shear, it's trying to rotate it clockwise. This would be a negative shear, it's trying to rotate it counterclockwise. So even in a beam, that shear convention only works with looking at the vertical cuts. And even when they get into doing the horizontal shear, they really just throw out the convention. Even in this book, they're just like, don't bother. Just find the vertical shear and just know that the horizontal shear, I mean, basically that's the whole idea, is when it comes to shear, is like if you find one, you know them all. And so they try to teach the convention that if you see that this one is arrow up, that this has to be arrows touching, and then if this is tails, see how tails touch? And then, but that's a dumb way, you know what I mean? I would do it 100 ways this way. If I know that this shear stress is up, it's associated and it's acting on that area, and never forget that this is a three-dimensional cube. So that's associated with a force up. Newton's laws and forces in the y have to be 0. So over on this face is the only location I can have a vertical force, because these are going to be horizontal due to the shear. So I'm going to have a shear stress down, causing a shear force down. So this one's up, this one's equal and opposite down. That's going to cause this moment. So we need something to balance this moment. And that's going to be, so the moment's going to be this way. So these forces, one's going to be this way and one's going to be this way. And they're going to be equal and opposite because they're also going to be a couple. And their magnitude has to be equal to these because these two forces are the same and they're this distance apart. These two forces have to generate that same couple and they're the same distance apart. So that couple has to be the same. And so that's how I would, anytime I have one shear stress, I'm associating it with a shear force. And I'm saying if I have this up, the best way to do is go to the other side and say I must have one down. That's some of the forces in the y direction. And then some of the moments. This is causing a couple, so then I have to do these. You know what I mean? And if I just had one, hey, I could resist that couple, but now I have a force in the negative x, and I got to balance it with a force in the positive y. So there you go. Some of the forces in the x directions are also 0. All right, booyah. So hell yeah. So we're in the zone of making a cut. And then analyzing, so this is what we do. So we make the cut, we know that these are stresses, they're acting on areas, and so we can do a force diagram right here. So we've already said that this area was the area A naught tangent theta. Let's figure out what this one is. So this one's cool. I use the trigonometric trick. Well, I mean, let's say you know, like in trigonometry, the easiest one is when you know the hypotenuse. This comes up a lot because maybe this is a vector, and I just know the magnitude of this vector, and I want its components. I want its vertical component, and I want its horizontal component. And those are going to be percentages of the hypotenuse. The hypotenuse is always the larger number. If I said this was 100, percent, it looks like this is about 80%, maybe 85%. It looks like this is about, maybe this is 80% and this is 60%. And I got a 3, 4, 5 triangle. That's basically what it looks like. Because if I cut this in half, I can see, hey, this is more than half. It's about 60% of this hypotenuse. Okay, so if we know that, if I take this bigger number and multiply it by 80%, I get this. If I multiply it by 60%, I get this. So let's say I knew this length, and I knew this length was 80, and that's all. But I wanted to know the hypotenuse. Now what do? Well, I take this length and I divide it by 80. Yeah, I don't know if that actually made sense. But if I take the hypotenuse and to find this is the angle, do some sun shining rays. That means that this is the sine component. The angle always shines on the sine component, and the cosine component's adjacent. So if I know the hypotenuse, this is going to be the hypotenuse times the cosine of the angle. And just think the cosines and sines are percentages of the hypotenuse. Cool. So the bigger number times cosine of the angle, a bigger number times a smaller number, is going to give me this smaller length. If I know the smaller length, I can, and I want the hypotenuse. I know they're related, so I just think, hey, cool, they're related by the cosine. Here's my angle, and I know this is the adjacent, so they're related by cosine somehow. And so this is the smaller number. What would I do to get the bigger number? And so I don't take this smaller number and then multiply it by cosine, because cosine already is a percentage. It's already it's a fraction between 0 and 1. So what do is I take this length and divide by cosine. And so I think that is one to throw in your wheelhouse just to be able to spit out. If I'm like, hey, I want to know the hypotenuse, and I know the cosine component of this angle. So I'm going to take this length and divide it by a smaller number. A number divided by a smaller number gives you that bigger number. So cool. So this dimension is A naught divided by cosine theta. Now, 1 divided by cosine theta is secant theta. And that's the only bummer. I mean, it's fine. It's fine. But like my first go around is just like, I don't like that. I don't like that they use secant. It seems like there's no reason to ever use secants or cosecants, because if it's a textbook, sure. I mean, you're just writing text. You probably have to write it like this because it's a bummer to throw in a graphic and divide by cosine theta. But just visually, if I'm reading this, I'm saying A naught divided by cosine theta. That's what secant is. And that really shows that, hey, that's this length divided by that smaller number that gives me that hypotenuse. And again, don't forget that this is a cube. And so when we say that the length of this line is A naught, we're referring to the length, the height of this line, and then the depth into the page. Cool. So now we have this area down here is A naught tangent theta. This area right here is A naught divided by cosine theta. And they're going to say 1 divided by cosine theta is secant theta. So that's where that comes in. And then that diagram below is a force diagram, because if here is the stress, I know the shear force right here is just this shear stress times that area, times A naught secant theta. This is going to be associated with a normal force, and that's going to be sigma x1 A naught secant theta. Now these two values are the ones that we don't know. These are the given quantities. And so the only other trick that saves face when setting this up is to, we have this angle and we have a new axis, x1, y1. So when we sum the forces, we want to sum the forces in the x1, y1 direction. It seems tempting, to sum the forces in the x and y direction, because it looks like we've got 4 different things in the x and y direction. But in the end game is to solve for sigma x1, and we hella do not want to break this up into 2 components. If you sum the forces in the x direction, let's say, well, you're going to have to break this up into the x, and you're going to have a component in the y. And so since we're solving for sigma x1 and tau x1, y1, we have to set this as our new x direction. So we're going to sum the forces in x1 and sum the forces in y1. So then you get these two equations we're going to go over. The trickiest part is to figure out what this second, we have the force. This is a stress times the area. So we have that A naught tangent theta, so we can recognize that from what we were talking about. And so this is the force, and this is going to be a component in one of the directions. And so we're going to sum the forces in the x1 direction, that we get this equation. Sum the forces in the y1 direction, we get this equation. Now, I kind of came up with a few different, ways to solve this because, all right, so let's just go over it. Let's sum the forces in the x1 direction. So we're going to have this force, and this is already the force diagram. So we know that this surface is A naught, so this force is sigma x A naught. Got it. This force is going to be that stress times A naught, tau xy A naught. So that's what we have. We know the area down here is A naught tangent theta, so that's how we have these forces. These are forces, stress times the area. So we have tau yx times A naught tangent theta. Sigma y A naught tangent theta. All right, so if we sum the forces in the x direction, we're for sure going to have this. So that's the first term. Sigma x1 A naught secant theta. So that's what we have down here for our first term. The second term, they're going to use this face first, and they're going to do the normal stress, and then they're going to get so let's do this one. They're going to go here, here, and then they're going to go here, here. And so we need basically the percentage of this force in this x1 direction. And we can already see that it's in the negative. The component of this force is going to be in the negative x1. So you know what I mean? So right here we have a negative. We have this force, sigma x A naught. That's what this is. And so now we just need to know whether it's the sine or cosine of theta. And so one cool way that we can look at this is see how this is a 90-degree angle, and you can almost think of this as like a sheet of paper, like a corner of a paper. Let's rotate this back, into its original x and y axes. And then as we rotate that up, this corner of this paper, as we rotate it up into x1, this distance theta, hey, this angle is also theta. So from the horizontal, we have an angle theta. And then from this vertical, we have an angle theta this way. And then also, if I extend this x-axis this way, and then have this as, I can see that this will be theta, and then this will be theta. I call this maybe like the bow tie approach, where it's just like, hell yeah, it's good to see where this angle kind of pops up in the easiest locations. And so, and then we're going to have, from the vertical, we're also going to have this angle theta happen. And this line will also, if we extend the y-axis down, and we extend this y1 here, this angle will also be theta. So it's kind of like a little bow tie. So then we can figure out, we can use one of those. So if this is a horizontal force, I'm going to look at this horizontal line and say, hey, the angle goes up here, and I have this. I could use this as my bow tie, or I could use this angle as my bow tie, or theta. And so this horizontal force is going this direction, so I'm going to use this angle as my theta. So now I'm going to visualize this angle theta. The sun is shining on the vertical component. The vertical component is in the y1 direction. So I need the cosine component of that. So cool. So now I know that this is going to be in the negative x1 direction. The force is sigma x A naught, and I'm going to have the cosine component of theta. So that's where we get negative sigma x A naught cosine theta. Cool. Now we're going to move on to the vertical one. And then you're just like, well, are we going to use the same horizontal force? Hell no. We're going to use the vertical force. And so if I do this and this, I can either use this as my little bow tie or this. And so which one do I want to use? Well, I'm probably going to use this one, because if I come here, and you can even see, this is probably pretty easy. This is a parallel line, and this is a parallel line, and then I kind of use this Z shape. I call it Zorro, you know what I mean? Where, hey, this angle theta right here is the same as this angle. Cool. So then I know that if this is the angle, I put some sun shining rays on it, this is going to be the sine component. And then this is going to be the cosine. Cosine component's in the y1. The sine component, hell yeah, that's going to be in the x1. So this next term is going to be the negative direction, tau xy a naught sine theta. And so that's what we have here. Negative tau xy a naught sine theta. And this is brutal because it's really difficult to see where these angles are with just like, you know, this angle given and this angle given. All right, so now the next term is this. If I see, this is going to be in the negative x1. It's a vertical force, so I'm going to go down and then here. And then so I'm going to say, hey, if this is my angle, the bow tie of it's over here. So sweet. And I'm going to say the sine component's this way. Hell yeah, so that's what we have. And we're going to have negative ay. Now, is that, yeah, that's going to be right, because this would be the cosine. Cosine would be y1. I've messed these up before, too. But this is going to be the sine component. So we're going to have negative sigma y a naught tangent theta time. That's going to be the force, and that component of the force is going to be sine theta. And hell yeah, that's what we have here. This sigma y a naught tangent theta. And then that's going to be the force in the negative x1 direction, and the component of that force, the percentage of that force, is that sine theta. Cool. And we're almost done. Last one is going to be the shear. It's a horizontal one, so here's our bow tie here. So we could use this angle, or we could bow tie it this direction. So we'll probably do that. So we're going to bring it down here, and then so this would be our angle. And we want to know this component. So the sun is shining on the vertical component. That's the y1. So we need to know the cosine component. Cool. So this is going to be negative tau yx a naught tangent theta cosine of theta. And that's what we have here. Negative tau yx a naught tangent theta cosine theta. It is good, I don't know, to get used to just reading just technical jargon. All right, hell yeah. And we're, you know what I mean? Let's see if we can speed it up a notch and try to get the other, so we'll try to get this all on one page. We're going to get this equation. We want to sum the forces in the y direction. So this force, this is a force, right? It's a shear stress on that area that we talked about, a naught secant theta. That force is all in the y1. So cool. That's just going to be all that. There is no component, you know. So cool. And then we're going to do this one, this one, this one, this one. And so hell yeah, a horizontal. Here's our angle. We're going to bow tie it this way, and I want the sine component. Sigma x a naught sine theta. Hell yeah. This one, it's a vertical, so here's our vertical angles. I'm going to bow tie it this way, and we're going to do the cosine. So tau xy a naught cosine theta. And it's going to be negative, sorry I didn't catch that, but yeah, negative direction. And so that's what we have right here. Next one is going to be this sigma y. So it's in the negative y direction. It's a vertical force, and so I got my little bow tie. And it's going to be the cosine component, because the sine component is in the x1 direction, cosine. So minus sigma y a naught tangent theta cosine theta. Booyah. And then the last one, horizontal force. So here is my bow tie. And what should we do? We should, bow tie it this way. And so we have, it's going to be positive, and we want the sine component, because this is the vertical component, or the sine component. And so we have positive tau yx a naught tangent theta sine theta. Booyah. All right, so we have our two force equations, and everything is known except this sigma x1. That's the whole idea. The whole reason we did this is we just want to know sigma x1. And we did a good job because it's just all variables. These are the 4 inputs, and honestly, this is just 3. It's a normal stress in the x, a normal stress in the y, and a shear stress. If we know one shear stress, we know all 4 shear stresses. And this whole chapter is just on plane stress. So this chapter is saying, hey, this surface right here in the z direction doesn't have any shear, and it doesn't have any normal stress. And this is stuff that is hard to pick up from the literature. It's the surface of a beam might have axial stresses, cool. But if that surface doesn't have any load on it, like any cars or snow, it's just the surface of the beam, and maybe the bridge actually has a lot of weight, so you are getting shear stresses. But there is no shear stresses on the surface of a beam. So that would be, if this was the top surface of a beam, there is no axial loads on the top surface. So on the surface of stuff, this applies always. And so you can always take this little element on the surface of something, and that's what this chapter is like a plane stress. And pressure vessels are that way too. It's kind of fascinating. Where on the surface, there is no stress, but you do have stresses like a bubble trying to pull it apart. Cool. All right, but anyway, so we have these two force equations, and they're equal to 0. Some of the forces are balanced, and we're going to solve this one for sigma x1. One thing we can notice is that there's an area A naught in all of them, so we can just factor that right out. The other thing we can do is get everything to the other side. Everything's negative on this side, everything becomes positive on the other side. This is 1 divided by cosine. So then we're just going to multiply the other side by cosine. So just pretend all these terms are positive and on the other side of this equation, and we're just going to multiply them by cosine. So this becomes cosine squared. This becomes sine theta cosine theta. Tangent is sine divided by cosine. So, and we're going to multiply by a cosine. The cosines cancel. This becomes sine theta squared. This is going to be sine theta divided by cosine. So this cosine cancels that cosine in the tangent. And then we're going to multiply by another cosine. So we're going to have sine theta cosine theta. So up here we said we had sine theta cosine theta. Here we had sine theta cosine theta. All the a's cancel. Excuse me, more water. These are the same terms. So we're going to have -1, and sorry, all these are positive now. So we're going to have one of these added to another one of these. So we're going to have 2 of those. And the A naught, these are all positive, taken to the other side. The A naughts are canceled. And so we have 2 tau yx sine theta cosine theta. And then we have positive sigma x cosine squared theta, positive sigma y sine squared theta. And that's going to be sigma y1. So we did it, you know what I mean? And so, because they don't spell it out for you. They just say, hey, this becomes that. And so we have 2 of those. We just talked about that. We have that cosine squared times sigma x, sine squared times sigma y. Booyah. All right, let's play that same game for this one. Now so we need to get these terms to the other side. So these become positive, these become negative. All right, and then we have this is 1 divided by cosine theta. So we're going to multiply the other side by cosine. A naughts cancel everywhere, or factor out, however you say that. So if this is negative on the other side, and we're going to multiply by cosine, we're going to have sigma x sine theta cosine theta. Let's do the other sigma y. This is going to, and that's going to be negative. This is going to be positive sigma y. Tangent is sine divided by cosine. Cosines cancel. We're going to have sine theta multiplied by that cosine. So we're going to have sine theta cosine theta. Cool. And so you could say, so keep that in mind that these both have a sine theta cosine theta. So we could factor out the sine theta cosine theta and say this is sigma y minus sigma x. And then sure enough, they're going to do something stupid and put that in parentheses and put another negative and switch the order. And they're going to say it's sigma x. It's going to be positive sigma x minus sigma y. But to get these to the other side, this becomes negative, this becomes positive. So keep that in mind. All right, this goes to the other side positive. And this is going to be cosine squared. So we're going to have tau xy cosine squared. When this goes, so tangent is sine divided by cosine. And so when we multiply this by cosine, the cosine will cancel, and we're going to get sine squared. So this becomes negative sine squared theta tau xy. And tau xy and tau yx. Tau xy and tau yx are the same. I should have mentioned that up here. So that's how we could add those. So at any point you can just say these are the same. You know what I mean? Even on this diagram, you don't have to call this tau yx. You could just call it tau xy, and because they're equal. Anyway, they carry all that through and then make the association right here that tau xy is equal to tau yx. Cool. So we caught that. Yeah. So this, what we would say, the cosine came. So this is sine squared, and then and so we have so this is going to be negative tau xy sine squared theta. This is going to be positive tau xy cosine squared theta. And so cool. Let's see what that is. So this was going to be positive tau xy cosine theta. Getting this to the other side becomes negative tau xy sine squared theta. This is where it was a bummer. This should have been negative to the other side, but they're going to put this in parentheses, so it still is negative. It's negative sigma x. And then this negative makes this positive sigma y. So taking this to the other side becomes positive sigma y, sine theta cosine theta. And but they just want it like this because they want the difference between sigma x minus sigma y. Then you can use these trigonomic identities. You can be like, oh, cosine squared theta minus sine squared theta is going to be, hey, this is cosine squared. So this thing is cosine squared theta, and we're going to subtract it from this side. This is going to be a 1/2 minus a 1/2. So the 1/2s go away. This is going to be cosine 2 theta minus a negative cosine 2 theta. And I'm sorry, I didn't factor through the half. This is going to be 1/2 cosine 2 theta minus a minus 1/2 cosine 2 theta. So we're basically adding a 1/2 of cosine 2 theta to a 1/2 of cosine 2 theta, which becomes cosine 2 theta. So this part becomes cosine 2 theta. That's how they do that. And if I had more time, I would actually, this is a fun one to do. It's a double angle because we have this. And so you set up two angles that are theta theta, and you're trying to find the cosine of that double angle. And to do that, you say, you first do the cosine, and then the cosine, and that overshoots it, and then you do cosine, and then the sine. So it's cosine, which is cosine squared minus sine squared. And then you turn sine squared into the 1 minus cosine. Anyway, so yeah, it's just, that's a fun one to do. Do it on your own time. But else, like how the hell, that one is good. I think I've made a video on that somewhere. Cool. And this combines two of those half-angle identities. You know what I mean? Well, that half-angle identity has a cosine component and a sine component in it. And so you can solve either for the cosine squared theta or the sine squared theta from that one identity. And then you can plug both of those into there. And what you're doing is you're getting rid of the cosine squared part, and you're just having it in terms of a just a cosine, but not a square of a cosine. So hell yeah. So that's the whole idea behind that, simplifying that. This sine theta, cosine theta, same thing. This is almost like a sine squared, cosine squared, even though these are different. What we really want this is just as one term. And so we can use the same, sine of 2 theta. If I had two angles that were theta theta, the sine of that is going to be this vertical part. And I would say that's going to be the cosine, and then the cosine component, and then the sine component. And then it's going to be the multiplied by the sine component, cosine component. So adding those. So sine theta, cosine theta, plus sine theta, cosine theta equals sine 2 theta. And so that's why two of those over here equal sine 2 theta. So that's pretty good. It's even good to do those mentally. So, sorry, I should have paper here, but the whole idea is not get carpal tunnel and just talk our way through this stuff. And which you should be able to do anyway. Like even if that didn't all settle in, it's just like, yeah, that's the whole reason you do something on paper, do a proof, and then so you can see if you can mentally get there. And still not just look at this as an identity, but to visualize where that identity comes from. Because you're setting up a double angle, and that's two angles, theta, theta, so that's 2 theta, and you're taking the cosine component. Anyway, so hell yeah, when we do all that, this gets divided by a half, so this part gets divided by a half, and we get to throw a sine 2 theta in there. Okay, so hell yeah. So let's since we were talking about this one last, let's do that one first. So we have that divided by 2, and we have that sine 2 theta. This became cosine 2 theta, and now we have our equation. But I mean, this is so far from reality. I mean, just the fact that an equation is nice and tidy, and it's in simplest form, is just far from the understanding of where we, you know what I mean? Like, this equation is actually probably better. If you took all these terms to the other side and even included the a naught, even though that's irrelevant, and then just divide it by a naught secant theta, and if you just said that was your sigma x1, and you didn't simplify, I mean, always think about that too, especially when equations get like way simplified. I mean, I can't tell anything from this equation, but this equation, hell yeah, you can still see that you have a stress times an area. This must be a force, and this must be a component of that force in a particular direction. You know what I mean? So this you can see where, and you literally can. You can just take all of these 4 terms to the other side and divide by a naught secant theta, and keep the a naughts upstairs and downstairs. You know, even though they all cancel out, but you'll have a better understanding of where that this equation comes from. And if you did your first equations from that, that's a good way to actually get used to the proofs. So if you have if like one of the problems says, hey, I have this going on, and I have a tension, and then I have a tension in this direction, and I also have a shear. Find the maximum, or just find the rotated stresses at 20 degrees. Like, that'll be a problem. You know what I mean? So just come down here, do your 20 degrees, and then, have this just as your variable, and do that same process. You know these, and you basically would just write these two force equations. And after you write and you don't even need a moment equation, because you rotated your axis. So sum of the forces in the x, this is the force in the x. Sigma x1 a naught secant theta, the stress times that area. And then just divide, and then figure out what the other ones are in the x direction, and then just divide it by a naught secant theta. And you found your stress in your rotated stress. You know what I mean? Else, and I'm glad I explained that, because what's going to happen is you're going to throw all those terms into here, but not realize, like, I don't know, you're just not going to understand. Like, I don't even understand where this, you know what I mean? I just, like, even I mentioned this with like 2 pi r, like, just how dumb that is, because that's the circumference of the circle, 2 pi r, but it's all mixed up. It should be 2r pi, or pi. Sorry, so it should be pi 2r. It shouldn't be 2 pi r. It's just and there's a lot of things in this book that are like that. You know what I mean? They're just like, hey, area is going to be maybe area B times area C, and then you're going to you know what I mean? And it's going to be a moment with area A, and so they should write it as B times C times A. It's the area, you know what I mean, causing a force, and then times a distance. But then you just rearrange, like, numbers and symbols in just classic ways, where constants, numerical integer constants, are always in front. And so if the circumference of the circle is pi d, and d is 2 times the radius, the circumference of the circle should be pi 2r. It should be written like that, but it's not. And that's just a small example of how, if you rearrange an equation, it loses it loses like how you got there, like, real fast. Quadratic equation is one that I despise. I don't mind using it as a double check, but I just use the square, like, you can derive the quadratic equation in about 3 steps to actually get something that says x over here is equal to all this stuff. And the only reason the quadratic equation looks the way it does is because you got to do 3 other steps to simplify it. All right, so enough said. So you'll be using these equations. You're just going to throw in, hey, some tension or compression in the x, tension or compression in the y, and some positive or negative shear. And in positive and negative shear, we talked about what a positive face is, but it's also, from chapter 2, is if you take your little square or your little cube, and it's a good idea to always sometimes, like, hey, put your axes like right here. And then, especially when you're doing shear, trying to find shear angles, positive shear makes this turn into a diamond shape in that first quadrant. You know what I mean? So, oh man, 562. Let's go there, because I can find this fairly fast. And it's good for me to... Oh, hell yeah, I think I did it pretty fast. I was still not there, though. All right, chapter 1. Oh, bummer. I probably passed it. But no, we'll get there. It's a good one to look at. Huh. might passing it up. Sorry about this. We'll get there though. Yeah, it should be just right here talking about shear. Maybe it is in chapter 1. No, that is. Sorry about that. Yeah, it totally is. All this stuff's in like 5 different places. Chapter 1 has shear. Chapter 2 has shear. And so, hell yeah. So here's the very first chapter in this book. You do this element. And what happens is a positive shear causes it to make a diamond shape in this first quadrant. And it doesn't show what negative shear is. And so I don't even know why it even came here. But to actually draw this shape is, I would say that, hey, this is your pivot point. So this isn't going to move. And the only 2 forces that are going to cause distortion are these. So when drawing this, I'm going to say, and then the other aspect of shear is that these lengths don't change. So it's like a cardboard box that gets collapsed, and so it turns into a diamond shape. But it leaves it creates the same angle here as it does with this wall. So don't just think that it goes straight up like, you know what I mean, the picture of this bolt in shear. The picture of this bolt looks like it just goes straight up and straight down. But if we take a small little element kind of right in here, it's going to cause a diamond shape, and that diamond shape is going to look like this. And so to draw this shape in just 2D, how I do it is I say this length is going to move up, so I just make a dot right here and a dot right there. I say, hey, this length is going to move over, so I make a dot right here and a dot right here. These 2 are just ready to connect the dots from here to there. But because I have 2 different dots up here, I just square them and I put a dot right there. So to draw this shape, this diamond shape, I'm going to go from here to there and then up to that top square. And then I'm going to go from here to here and then up to that top square. I don't know if this is very useful to like not have a stylus, but you know what I mean? I'm doing it, and we'll get better and stuff like that. But hell yeah, it's fun to visualize. So anyway, so this length moves from here to there. This one moves from there to there. But obviously, these 2 lengths have to meet, so we meet right at this square right there. So that's how you draw that. Because sometimes that diamond shape's difficult to draw. And so that's what that diamond shape is. We moved up there, and then we moved up there. Now, this one also moved, you know, up, and this one moved over. But we have to, you know, kind of complete that square, if you will. So it would be right there. And so that's where we have it. Hell yeah. All right, so let's go back. See if we get close. All right, so we have our 2 equations, and yeah, you can just, so here they are. And then so we did our trigonometric identities, and now here are our equations. So if these weren't too confusing, you know what I mean? Like, yeah, I even looked at these and I say a lot gets lost in these equations. And then once you throw in the trigonometric identities, you're just like, holy Toledo. You know what I mean? They don't look like, you know, I guess you just trust them and you make sure you don't mess up a sign change. But if you're like, we'll see if we do it in this video, because a lot of these is just like, they're going to be asking for these stresses at a particular angle. And it would be nice to even just have a hunch if it was negative or positive, right? You know what I mean? And so we can even look at that if we wanted to. You know what I mean? So the way you do that is don't lose, you know, you have this initial stress, and if you wanted to make an angle, you know what I mean? Hey, let's say you're going to take this angle from theta, and doing that this way is going to be a face that way. So, I mean, so yeah, so this is a good picture to do, even though it's not as obvious. But if I'm going to rotate the angle theta, I can make the angle from this vertical. And I know that these are stresses on the faces. I know this area gets reduced. And so you can just do that. Like one of the problems is, well, I guess we'll do it when we get to it. But hell yeah. So now we have these equations. Let's see what we're going to do with them. All right, so how did we get that other one? Oh, yeah. So we solved for sigma x1 and the shear x1, y1. It would be useful to actually do a, to find the other face. How we would do that is if we said this was our angle theta and we just found this face, this normal face, we need to find the other side. And so what we could do is make this our angle theta as well. Or you could just say, if this is the angle theta and I lopped off this part, just lop off this part. But that's gonna, it gets a little horrendous because, well, these are all stresses on A naught. But then again, like, hey, if you have a cut this way where this is your angle theta, you need to find this area because these stresses are going to be on that area. And we said that if this is angle theta, and I know this, hey, I'm going to use the tangent of this angle. I want to know this opposite, this little slice. And so the tangent of this angle is this divided by that. And so I'm going to take that to the other side. This is on the bottom of the equation. I can take it to the other side, so it's A naught tangent theta is this angle. But if I take my cut right here, which is going to have a normal force in this direction, oh, and I'm messing up, man. Yeah, that would just solve for the sigma x in the negative direction, or you know what I mean. I guess if sigma x is positive this way, it would just solve for sigma x. What we need is a 90-degree cut. So if this is our angle theta, we actually need to rotate that 90 or just perpendicular. So if I'm taking this cut from this vertical, I actually need to take a cut from the horizontal. So I could take this cut right here. And that would give me, because if we said that we're trying to rotate this where this is x1 and this is y1, then I'm going to take this as my cut, throw away this top part, and then use this will be A naught, this will be A naught tangent theta for the area, and then I would have this y1. But what they choose to do, which is kind of interesting, is knowing that we can, since we found x1 as a function of theta, we could rotate it up 20 degrees. We could add 90 to that, and we could rotate this face 20 plus 90. So that would mean that this x1 face is up here. If this x1 face is up here, the y1 face is over here. You know what I mean? That doesn't change. But if we rotate this x1 face from 20 up to another 90, that's going to be 110. That will give us, and then if we solve for x1, that will give us the stresses on this face. Which, so if the question says, hey, find the stresses at 20 degrees, we can use the two equations that we just derived. But if we want to find y1 when theta is 20 degrees, we're just going to say theta is 120 plus 90. We're going to say theta is 110 degrees. Solve for sigma x1. And then just call that sigma y1. So that's what they do from a mathematical standpoint in this, to get this sigma. Oh, so those are the ones with the trigonomic identities. And then to get sigma y1, we're going to throw in theta plus 90. And if theta is 0, let's say if theta is 0 on cosine, this is 0. But if theta is yeah, so and don't forget, these angles are going to have to be multiplied by 2. So the angle that you choose to rotate the element, that's theta. And then you have to multiply that by 2 in this equation. So if theta is 0, 0 times 2 is still 0. Cosine of 0 is 1. And if I say theta is 90, 90 times 2 is 180. And another way to do this is just do a grid. And so, and here's a triangle with 0 degrees. It's just a line, and that's all cosine. No sine component of that triangle. That's 0 degrees. If I go 90 times 2, that's 180. So that's going to be a triangle this way. And then that means that the cosine component is in the negative x direction. So if I go theta plus 90, this term will become negative. Now, that's not so obvious with this next term. So what I kind of like to do is like, hey, let's go back to this cosine term and throw in 5 degrees. So just a shallow angle, and I'm going to multiply that by 2. So now I got 10 degrees. The cosine component of that is positive. Cool. Now I'm going to add 5 degrees plus 90. That's 95 for theta times 2. That's going to be 190. And so my angle is going to be 190. It's going to be down here. And then my cosine is negative. And it's going to be the same as this, just with a negative sign. So now we can do that with the sine theta. Because if I just threw in a 0 here, sine of 0 is 0. And if I threw in a 90, 90 times 2 is 180. Sine of 180 is also 0. So it's hard to tell if this changes at all. So if I get my grid and throw a sine of 5 degrees, or if I throw an angle of 5 degrees, 5 times 2 is 10, I'm going to have 10 degrees, and the sine component's going to be positive. Then I'm going to add 5 degrees plus 90 to do that rotation to get the sigma y1. That's why we're doing this. 5 plus 90 is 95 times 2. That's going to be 190. So I'm going to go a distance of 190, so it's going to be down. And look at that. Sine is now going to be negative. So if we're going to add theta plus 90 to this equation in these two thetas, this is going to become a negative, and this is going to become a negative. Negative sine 2 theta. This becomes a negative cosine 2 theta. So that is what we see for sigma y1. So that's the only difference between sigma y1 and sigma x1. All right, so it says summing the expressions sigma x1 and sigma y1. If you do that, even though they look complex, this has a negative tau xy sine 2 theta. This has a positive tau xy sine 2 theta. So when you add these equations, those two terms drop out. This has a negative, this part. This has a positive, this part. So when you add these two equations, that drops out. So hell yeah. And this is going to be 1/2 sigma x, 1/2 sigma y. And so this is going to be 1/2 sigma x and 1/2 sigma y. So when you add those halves, you're going to get sigma x plus sigma y. So hell yeah. So and that's it. It just it just shows you like it's a check on reality, and it's, I don't know, I guess it's just the nature of these transformations that and it's the only thing that actually makes, I don't know, it's kind of one of the only things that makes this tolerable, especially when you get into more circle, and especially when you're trying to find the max stresses. Well, it basically says like if Well, it's useful in this fact that you can kind of have checks on realities that these two, when you do something at an angle, the normal stresses, 90 degrees in the x1 and y1, those are going to add to the same normal stresses that you started out with. All right, so enough said there. So it's just maybe useful to have checks on reality. Okay, so this diagram is for, whoa. Yeah, this diagram, they're just going to choose different values. So you're going to have a value for sigma x1, and it's going to be a rotated element. So, right here, you have if you have a value for sigma x, your sigma y is 20% of sigma x. That's what you're starting with. And your initial shear stress is 80% of sigma x. So you have like all three things, and everything's positive. So you have a positive tension, you have a positive in the x direction, positive tension, 20% in the y direction, and then you have a shear that's 80% of the psi, or pressure, of your normal stress. And what we see from this, at 0 degrees, we don't get a max. You know what I mean? Here's our sigma x, and then our sigma y. I don't know why they do diagrams where they don't throw I don't think it would overly complex, you know what I mean, to throw sigma y on here. But they just said that if theta is 0, sigma x, and so that's this one, sigma x is going to be right there. And that value is going to be, yeah, sigma x. Cool. And 20% of sigma x is sigma y. So there's sigma y right there. So if we drew in sigma y on this graph, it would show up right here. What they just show is that the sigma y is 90 degrees to sigma x. And that's a bummer, because I don't know exactly why. But at 0, but at 0 degrees, sigma y would go through here. And check this out. At 90 degrees, all this stuff repeats anyway. Is that true? Damn it, I don't think that's true. So in this direction, oh no, this is, okay, so this is, but yeah, I wish they threw a sigma y on here, because sigma y should be right here, at theta. So if we had three lines, you would have this sigma x1, you would have another one, sigma y1, and it would go through this point right here, and then you would have the shear. And what they're showing is that, hey, you get a max normal stress, sigma x1, right here, and then you also yep, and what happened, and from here, I guess we're going to be talking about shear in a moment, hopefully not an hour, but at 45 degrees to this point. So this can happen at any angle. So this maximum happens right here. Let's say that's about like 40 degrees. Because it's not 45, because this is the max shear, and it happens, this max shear happens at 45 degrees to this max normal. And so if this is like 40 degrees, then this happens at 85. And it even looks like this is 80. So 80 minus 45, so this would be about 35. So this max happens at 35. At this max, and because this is 45 right here, at this max, our shear stress is 0. So that's the other thing that happens. So anytime your shear stress is 0, your normal stresses are maxed. And and we got this because sigma x1 and sigma y1 have to equal the original sigma x, sigma y. Okay, so those both are positive. I just wish they threw in sigma y1. You know what I mean? It just would have been, because so right here is 90, and so this would be the value of sigma y1 right here. You know what I mean? So if this value is maxed and this value is min, if this was the value of sigma y1, I would have this plus this is a negative value, and that's going to equal sigma x1. No, that's going to equal sigma x1 plus sigma y. Yeah, we got this. So this plus this would be a height right about there. And what I'm saying is that at this height, the other one, sigma y1, is this height right there. And so that height right there makes up that difference that I just said. Sigma x plus this sigma y would be right there, and that has to equal sigma x1 plus sigma y1 at this value. So that's cool. I guess I can talk my way through it. The fact that they don't show sigma x1 and sigma y1, we know, oh yeah, and from that equation, it's the same equation. Sigma y1 is just, I don't know if you call it, I guess you don't call it a transformation, but it's just this equation shifted 90 degrees. And so, and because of that, it's this equation shifted 90. So there you go. So at this point, this is the value of sigma y. So I can come to this 90, and I can say this sigma x, 90 degrees away, this would be sigma y at this point right here. So hopefully I got that right. Anyway, I just wish there's not a place in this book that they show a graph with 3 of those lines. So if you got a graphing calculator, do it yourself. Okay, so but that's kind of the gist of getting those equations. And so we'll see if I leave it there, because that's pretty decent. And I just don't want to run out of voice. We should probably do one example. Let's see, how far do we get? Because, and then they're going to show you uniaxial stress. Well, that's the same equation, except we don't have any sigma y. So we come up to, this equation, and you get rid of sigma y. Then your sigma x's cancel. No. Sorry about that. You have, because you have this component. So you have sigma x, half a sigma x, minus half a sigma x cosine 2 theta. And if you don't have any shear, then that's kind of what you have. So you have an equation with like 3 different things going on. Hey, maybe your shear is 0, that goes away. And maybe your sigma y goes away. So that's kind of all they're doing there for the uniaxial stress. If you just have shear, you just have that last part of the equation, you know what I mean, for both your sigma x1 and your sigma y1 and your tau x1 y1. Hell yeah. I think we're probably going to end it at this example, because the next part, even though I went over it today and I was happy, it's finding the shear stresses, and and that's a beast, because well, and finding the principal stresses, like where's the max. What I would choose for you to do is just throw these into your calculator. So if they say, hey, let's rotate, like for this example, they'll probably say, hey, let's rotate this at a 45. You know what I mean? Maybe they say 25, doesn't really matter. And you're going to get values for sigma x1 and sigma tau x1 y1. But maybe those aren't the max. So how you would find the max is just take these three equations and plug them into your calculator. And all you need to do is throw this equation and this equation into your calculator. And you would be able to find the maximum shear stress. And what you're trying to find is the maximum, maximum normal. I was confused those. But yeah, you're trying to find the maximum sigma x1 or the maximum sigma y1, whichever happens first when theta goes from 0 to 90. And so one of those, in the x direction, the sigma x1 or the sigma y, one of these is going to be bigger. But you don't know which, and you just want to do the graph from 0 to 90 because that's going to be your rotation. You're going to rotate the element from 0 to 90, and one of those is going to be the largest. And I think we just showed that if you rotate this one past 90, it just becomes the other. If you rotate sigma x1 to 90, it actually becomes sigma y1. And so we're just interested in graphing those two equations to 90 degrees and figuring out which one is the biggest. And that will give you the, for that next part, that gives you the principal angles. And one of those principal angles is bigger. Like both equations, you'll have two peaks. You'll have a sigma x1 at its max and a sigma y1 at its max, but one will be bigger. And so this equation will have two solutions for two angles, but one will indicate one of the bigger values. And so we're going to do that at another time. So for this, we'll go through these two examples and call it. All right, so hell yeah. So let's see what it even says. So we have we're trying to rotate at 45. Determine the stresses acting on the element inclined at an angle of 45. So this is the solution. So yeah, we're going to do it. If you wanted to do this the hard way, just cut here at a 45. Hey, this is going to be, we know what sigma x is. You know what I mean? And so let's say, like, because the numbers are up here, let's just make a cut here, lop off that part, and we know this area is the square root 2. It's 1.414. And then so you just do I would start not using this transformation equation. I would still start from the free body diagram approach and be like, hey, look at this. This 4,000 is going to be the same as that 4,000. And we have 70% of it from this in this direction, the normal direction, you know what I mean? And 70%. So we have a square root 2, 4,000. And so, and then if we just had the shear, because that's the easier one from chapter 3 or whatever, then we could say that this normal force is going to be square root 2, 4,000. But this normal force is over an area of square root 2. So the square root 2's cancel, and then we get that this force is equal to the shear. So the normal stress in this direction would equal to the shear. But because we have sigma x and sigma y, hey, we have this 16,000 also times 70% of it. Oh, no, sorry. We have this 16,000, 70% of that. And then we have 6,000, 70%. So it is useful to try to, you know what I mean? So let's just throw some numbers on these. So this is going to be 70% of this. I'm just going to divide it by 2. That's 2,000. And I'm going to say this is 3,000. I'm going to go 75%. So this is 3,000. I'm going to half this. That's 8. So this is going to be 12. I'm going to get that 75%. So we have 8, 3, and this comes 6. This is about 4.5. So we call it 4. So we have 3, 4. We can call this 4 and 4. We can call this 8. And then this is 12. So we can call it 20. So there's going to be 20 in this direction. And then so that means that the force in this direction has to be 20. But the stress is going to be 20 divided by 1.5. You know what I mean? So it's a third of 20. It's 20 divided by 1.4. So however you do that, it's actually. So what would that be? Is that just? I think the square root, if dividing by square root 2, is the same thing as, if you rationalize that, it's going to be multiplying by the square root 2 divided by 2. So yeah, 70%. 70% of 20, let's play the same game, and half of 20 is 10, so it's 15. We're just going to call it 15. So I think this normal stress is 15. Oh, look at that. It's 15. So you know what I mean? So I'm just, that is like the take-home point, is those transformation equations. Like, you going to remember those? Like the second you leave this class? Hell no. You know what I mean? So just and that's like every proof in this book is it, there's still some sort of Newton involved. It's free. It's some of the forces in the y, some of the forces in the x, and man, I'm just proud of myself from that moment right there, getting that. Just because it's like, yeah, it's like you want to have that intuition built in, and so let's see. And so the shear is going to be no, that was the normal stress, and if this was balanced, if this 6,000 was 16,000, it would be balanced, but it's not. And so these two forces are balanced, so that's not causing any shear. It's actually the imbalance in these two. So so this one is going to be in like that direction, 70%, and this one's going to be in this direction, 70%. So we're basically going to have this 12 minus 4. What do we call that? 4. So 12 minus 4 is 8. So we're going to have 8,000 in this direction, and we're only going to have 70% of that. So, or 75. So 8 divided by 2 is 4, and then 6. So I think this is a shear about 6. And yeah, hell yeah. So we have a shear about 6. And what direction would it be in? If it was on this face, it would be in this direction. And so if we had this thing rotated, I would have an arrow this way. So this is where I do not like this book. I would put in parentheses here because they're saying, they're not showing you the positive. Yeah, I'm glad I went over this one. I caught this one today. Is like, what do you think this says? Do you think this is a positive direction arrow that they're saying is a negative value? Or what they are saying is this is a negative direction and they're saying it's a negative direction. So you got to be careful with that. And so that's why if I updated this textbook, I would put little quotations right here as a way to say, hey, I have made the arrow in the negative direction, and I also want to write that it's in the negative direction. Because if you look at this shape, and here's our x1 and y1, so that's why going back to taking this axis down to this corner is very useful. Because now we can yes, this is the negative direction, and it's saying this is, this is in the negative directions. That's why I do not like that. I would rather have them do a positive arrow, keep everything positive, and say, hey, this actually turned out to be negative. I mean, isn't that what they're doing? Yeah, this is a typo, you know what I mean? Or just I don't know, you shouldn't confuse it any more than it has to be. But there's plenty of times where you do a normal tension, you just assume it's in tension because that's going to be a positive number. And if I had this positive arrow, and then there was a negative 15 right here, I would know that that's in compression. Yeah, so I'm sure throughout this book they actually do this, where they actually throw in compressive arrows and then also say the stress is negative, where they're showing you twice, but that can get not even redundant, but the negative times negative is always positive, so that I do not like. But anyway, so if you take the axis x1 and y1 to this corner, and you were to so pivot it on here and then go to these, if this shifts this way and this shifts this way, you get a diamond shape that forms in that quadrant. And so shoot, I didn't go over that, so I think let's go back to chapter 1:6. Hell yeah. All right, so we said that this was positive shear, and we even showed how to draw it. I forgot that I wanted to show how to draw negative shear. If this arrow is down and this arrow is that way, I'm still going to pivot it from this point, but what happens is that this side of the box shifts this way, so I'm going to draw a little point there and a little point there. So this point moves to there, this point moves to there. Cool. And then this shifts down, so this point moves to here, and then this point moves to here. And you can see that it's moving into the other quadrants. All right. And because this point moved to here and this point moved to there, I have to box it in right here. So this point now moved to there. So hell yeah. So now I have my points. So my parallel piped would look like this, to there, and then up to here, and then up to there. So there's my diamond shape. So I'm from here to there, and then I'm going to here, and then I'm going out to there. And then so the diamond shape gets squished in, and that's also one of the definitions of positive shear, is if how do they say that? If they say if like this angle, like in this case, this angle, like let's say in this case, this angle shortens because it becomes a diamond shape in that first quadrant. In this negative shear scenario, this angle widens. And I kind of forget how they want to say that, like which angle widens and which angle shortens. But I'm kind of done with what I just said. So hell yeah. So if that shape like kind of flattens inward, that's because these arrows are down and this arrow is to the left. And so now we can go back. All right, hell yeah. So that's what we have right here. So it is good and useful to take these axes and then take them to this corner, because when this shape gets misshapen from these shear stresses, I can do that same thing. I can pivot this corner. I'm going to kind of neglect these two arrows but go to these arrows, and I'm going to say, hey, this moves to here, this moves to here, this moves to here, this moves to here. These 2 points moved away, so I'm just going to say they met in this point right there. So now this shape looks like this, from there to there to there, and it looks like this squat diamond shape. And so that is associated, you can just see it spilling out into other quadrants. That's going to be, so that's another way to think about negative shear. And so I think that's pretty useful, because all this stuff is super heady, and it's just like, man, how do you keep on top of it? And I think you don't. I think you just, someone said, hey, there's this equation that you use, and it's called the transformation equation. And all you have to do is throw in 3 values, your shear, and I guess then you just have to figure out how to draw this. And so if you get the tau x1, y1, cool. It's either going to be a positive or a negative. And you know that if it's negative, this is the positive x1 face, and this is the positive y1 direction. So a negative shear is on the positive x1 face in the negative y1 direction. So that's why this is negative shear. But, hence the quotation marks here, because it's isn't that bizarre? I don't like that, but it would just be better just saying, hey, this is just quotation marks, instead of saying this vector is equal to a negative. It would be like, I don't know, I think that's bizarre. Because if you had a vector and then said it was a negative, no, I think it's, I don't know, actually. Yep. Yeah, you take that for what it's worth. But yeah, you're going to get stuff like that this negative number is associated with the correct direction this arrow is pointing. All right, booyah. So let's see how they do it. They're going to use those transformation equations, and they're even going to make it not even in one go, where you just take, if you're trying to find sigma x, hey, just throw all this crap in. You know what I mean? Well, we got 6 and 16 or something, and shear was, who cares? You know what I mean? And then your angle is 45. You know what I mean? Plug and go. Who cares? But what they're going to do is they're going to break it up. They're going to do, hey, this plus this divided by 2. So they're going to take the average, and they're going to do this minus that divided by 2. So they're going to get this term, and then they're going to plug and chug. So hell yeah. So our stresses were, a little more water. So we had 15 and 17. What's that going to add up to? 22. So 22 divided by 2 is 11. And then we're going to have 15 minus 7. That's going to be 8. And divided by 2 is 4. Or did I get that wrong? I'm probably getting tired. So this divided by 2 is 4. There you go. And then, holy hell. Wait. 15. No, over here. Oh, I'm looking at the wrong thing. I'm looking at the answer. So we have sigma. Yeah, and the only reason that worked out, that was cool. Sigma x plus sigma y is going to be equal to sigma x1 plus sigma y1. That's why these two added together, or the average of these, or anything, these two added together are these two. So hell yeah. So this is going to be 16 plus 6. That's going to be 22. Divided by 2 is 11. All right, 16 minus 6 is 10, 5. So we get 5, and then the tau is 4, and that's going to be positive 4. Cool. And then they're going to grab that sine 2 theta. Theta is 45, so sine of 45 times 2 is 90. Sine of 90 is 1. The other term is going to be a cosine 2 theta. So here's the transformation equation for sigma x1. So, this is that part, this is that part. Now we're trying to find these angles. So cosine of 90 is 0. And then we've got the sine of 2 theta is 1. So we're going to have 1 times the shear. The shear is 4,000. We're going to have 0 times this part. So 0. So we have 11 plus 4 is 15. So hell yeah, so we get that. Then, you know what I mean? And we could do the same thing down here for sigma y1. It's going to be negative 4,000. This part's still 0. And we have 11 minus 4,000. That's 7,000. And, I thought I nailed it or whatever. Oh, I don't think I actually solved for sigma y1 on this. I think we just solved for the shear, but you could have done, you know what I mean? We could have aced it and tried to guess for that. But anyway, so, and then the other one is, because I need to probably be done. So tau x1 y1 is going to be this equation. So we have, what do we have? We have this difference right here. So we have a negative 5,000. Sine 2 theta is 1 plus, but this is cosine 2. This is 0. So we just have negative 5,000. And that's going to be our shear. And let's see what got bigger. Hey, our shear stress got negative and bigger. our principal stresses got more average. So this wasn't, at a 45, this wasn't the max principal stress. And neither is this, because the max principal stress happens when the shear stress is 0. So, and how you would solve that, well, that's in the next part. You just take the derivative. One way is just to graph them on a graphing calculator and see which one's the biggest. Or you take the derivative, and that's all I got. I got to use the bathroom real bad. So we're going to be done. We went through one example, and hell yeah, this was pretty cool. Transformation equations. The next part is probably headier, for sure headier, finding the principal angles. Hell yeah. But I'm going to be done. Thanks for joining me, and that's a video.